All right. So I want to show you a couple things about Rust and why Rust is better than C. It is much more secure than C, and it's nice to see why that is. So you can install Rust with just a few Linux commands. And you can make a hello world application in Rust. So that's when you just think, oh, okay, I think everything's just right in this folder. Okay, let's just cat hello world and hello world. All right. Dot. All right, there we are. So that's the hello world. You just have a main function like you would in C, and then a print line function that just has Rust says hello. All right, and so if I go in that directory, there's a hello world here, and that's what it does. So that's pretty easy, and you compile it with Rust C the way you'd use GCC. All right, now let's try this integer app program. All right, and so here's my code. All right, so here I define I to be 1, and J, I specify what type of data it's going to be, U32 equal -5. And when you try to compile this, you're going to get an error message. And the problem is this is an unsigned 32-bit integer, and you cannot put a negative number in an unsigned integer. This, as you will see, is a very good thing in Rust. Rust protects you in ways that C does not. C will let you put the wrong kind of data in a box, and that's the problem with a lot of things. So let's take a look at the add app. All right, so here I set A equals 1, then I take A equals A plus 1, and then I print out the answer. And yet, when I try to compile this with add, I'm not allowed to, because this variables by default are immutable. They hold the number and cannot change. You have to tell it if you want them to be mutable, and this one is not declared mutable, so you cannot add 1 to it. So it's different variable types, and there's a link to a tutorial here where you can learn about them. But the data types are very important, and the way it enforces them is very important. So let's try an integer overflow. You see why Rust is better than C. So if you go up here, I've got ovc.c. Okay, and so here is a C program where I define an unsigned character X, which is going to be a single byte variable, and then I set it equal to a number, 230, and now I just have a loop where I add numbers to it, add 1, add 2, add 3, and so on. So that number is going to get large. Now, when I compile that and run it, what happens is it started at 230, then 231, 233, went up to 251. Then when I added more to it, it went to 2 and 10 and 19. And this is why C is such a dangerous language. The developer presumably wanted to count higher. They're adding more and more numbers. How is the developer supposed to know that when you add to 251, it wraps around like an odometer back to 2? Some people say C developers have an obligation to study the documentation, understand the variable types, and so on. And you can say that, but in practice, this is just very unintuitive. There's nothing in this code here that a developer can see that will tell them that when I add to this number, it's going to get smaller instead of bigger. They would have to remember somewhere else in the code it was defined this way, and this is the kind of integer overflow responsible for a lot of security flaws in C. And that does not happen in Rust. All right, so if we take a look at this one, this is the same program in Rust. I define a mutable, unsigned 8-bit integer, and I put 230 in it. Now that's the same kind of data type that I was using in C. And now I have a loop, and I just keep adding numbers to it and print them out. But the difference between C and Rust is Rust will not trick me. When I run that, it adds and adds and adds. And when I try to add to make it bigger than 255, then it stops and gives me an error message. This is much friendlier. The developer when you add something to it and the result will not fit in the variable, it stops and gives you an error message saying this is not okay. It does not blithely move forward and give you the wrong answer, which is cruel. You'll think your code is working and it will just end up having a security hole in it. Whereas Rust will tell you whatever you're doing here is wrong and your code should not be accepted in this fashion. You should go fix it, which is much better. All right. All right, and let's try string overflows, the most classic one. All right, so here I have a string. I give it 5 A's or 4 A's, and here I have a string and give it 4 B's. Then I print out the addresses of them and what the strings contain. Then I can have a new value for string 2. I read from input a new value for string 2, and then I just print them out again. So if I run this one, which is ST, okay. So A, B, 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 if I put a C here, then when I'm done, string 1 contains A and string 2 contains C. So that's all right. But if I put in a long string, then I got a new value for string 2. String 2 contained B. When I put a long value in string 2, it changes the contents of string 1. Now, again, consider the poor developer. Wait a minute, I just want to cat this program, which is string.c. All right, consider the poor developer here. They have 2 strings. Then they read a new value for this string. Now, how are they supposed to know that putting a value in that string will change this one? This is cruel and insane, and this is the classic string buffer overflow. It is, again, the kind of thing that is just extremely hostile to write a language that will do this, that without complaining will take data that doesn't fit and then put the data in the wrong place and corrupt memory and not tell you anything. And of course, this is because C was designed to be fast and to be very close to assembly language. So if you are a real expert and you know exactly what you're doing, it'll be the smallest, fastest code. But in practice, as we've seen over the decades, this leads to endless security flaws because not every developer is able to be as careful as they need to be to use C. So let's do it in Rust. All right. All right, so here's the same thing in Rust. I have a mutable string 1 and a mutable string 2, 4 A's and 4 B's. Then I just print out the addresses. Then I read a new value for it from standard input to replace string 1. And let's see what happens. Now I run this. All right. So if I put in a C, then notice it doesn't replace the value in this one, it adds to it. Well, that's not terrible, but it did not corrupt B. So that's nice. But maybe it would corrupt it if I had a really long input. And notice it doesn't do it. You put in a long input and string 1 just gets the correct value, all those C's added the A, and string 2 is not affected. Also notice the addresses do not change. This one is stored at 6688, and this one is stored at 6670. So that's only 24 bytes further along. And yet I added 32 C's. So you might wonder, how is it possible that I was able to put this long value in string 1 without leaking over into string 2? And you can tell by debugging it. GDB minus Q. You can debug the Rust program and you can list it. All right. And let me adjust this so it fits better. All right. So here is where it's going to ask me to put in new data. So I'm going to put a break at line 7 before that happens and run to that point. All right. And now I can examine this data. So I see string 1 is at this address. So let's see what's at that address. If I examine 2 hexadecimal words at that address, I find this is a pointer in memory, 0005555. This is a 64-bit pointer to a memory address. So the string is not stored there directly. a pointer to the string is stored there because I don't see the letters. The letters should be A, and that would be 41, 41, 41, 41. And I can take a look at the string 2. And it's the same thing. It's another pointer pointing somewhere else. So that's interesting. Now I can find out what's there with print S1. And that will just show you again, this will show you the pointer that is stored there, 5555 ending in 69D0. This value is the pointer where it points to. And if I look at that location, say 4 hexadecimal words at this location, there are the A's, A. And if I look at S2, again, it's got a pointer there. And if I examine that pointer, that's where the B's are, B. And notice that this pointer is at 69D0, and this one is at 69F0. So again, they're not very far apart. The data is actually stored here, and 32 bytes later is that data. In fact, if I go to the first one and just show more than 4 lines here, like 20, well, that'll do. Then you see here's the A's, and not too far along are the B's. So if I add more C's to the A's, maybe it'll overrun. So let's continue and put in a lot of C's. All right. Now it did not overrun. String 1 got long and string B is not corrupted. But if we examine where they are stored, they have moved. If I print S1, oh yes, it's giving me some trouble there. I think I made it, this happened to me before. Because I let it exit the process, I would have to, I think, put a breakpoint to get that clean. And let me see, I think I have a plan here. Okay, let's try it this way. We need to put a breakpoint at 10. And now run. Okay, and now continue. And now put in a lot of C's. There's 40 of them. And now I should be able to print S1 and print S2. And notice that, all right, here's the pointer. Let's see what's at that pointer. X/2X. Okay, there's the A's and some of the C's. And here's the other pointer. There's the B's, and notice it has moved this pointer. These things used to be separated by just 32. And what I did was change the pointer to point to a totally different memory region, very far away, where there's enough room. So this is what it ought to do. This is what many modern languages will do, like Python and Visual Basic. If you put a thing that's too big into a variable, it will automatically reallocate more memory somewhere else. It won't just ram in data that doesn't fit and change things you didn't intend to change, like C does. So that's why it works inside, which is what would seem like the obvious, simplest way to solve this problem. All right, and you can also compare command injection. Here's a command injection file, which is cmdi.c. I don't think I've got this one in here right now, but let's put it in. All right, so here I'm going to ask for an IP address and scan it from the user. And then I'm going to create a command line that says ping -C1 followed by the IP address that came from the user and run it as a system command. So this is a common but unsafe practice where you use a program to create a line of code, and then you pass that line of code to another interpreter that's going to parse it and run it. So if I save this one and GCC -O CMDI, all right, then I run that. If I give it an IP address, like 127.0.1, it sends one ping. But if I give it 127 and then a semicolon and LS, it executes the ls. This is command injection. I took data from the user that was just supposed to be some parameter under their control. And because I inserted this text without sanitizing it into a command line, the user was able to inject commands here. This is, of course, bash command injection, and under other circumstances, you get SQL command injection and all those flaws. And this, by the way, can still happen in Rust. It's a little hard to set up in Rust, but you will find that Rust does have the same flaw. It cannot prevent command injection vulnerabilities. They are at a higher level. You've written code that created a command line to execute, and you let the user change it so it is working as intended to execute that command line. So Rust is not the be-all and end-all for all possible security problems, but it is very good. And it does stop the most important problems like string buffer overflows and integer overflows.